So your book develops an expression for determining what the temperature of an object in the solar system will be given its distance away from the sun and what fraction of sunlight that it actually reflects. And so once you know how much is reflected, then the rest of the light is absorbed. The principle behind how this works is wherever you're at in the solar system, you're going to receive some flux of energy from the sun. And then the further away you are from the sun, the less energy you're receiving because it's going to fall off as an inverse square law with distance away from the sun. Like all the energy coming out from the sun is being spread evenly over spheres, and the area of the sphere is getting bigger the further away you are from the sun. So this object that we're thinking about is Earth. Earth is not going to come to the same temperature as the surface of the sun because, well, the flux of the Earth is not the same flux that's leaving through the surface of the sun. We're only intercepting a fraction of all that energy. Then Earth is going to reflect some of that. That doesn't impact our temperature. It absorbs the rest. And Earth will come to some temperature, and then Earth will radiate energy as a thermal radiator, sending out its thermal continuum spectrum into space. And that's what we're wanting to find, is what is the temperature of an object in the solar system. And the equation we're going to use is fairly specialized. So it is only thinking about our solar system and a sun-like star. So what that expression looks like, your book calls it the no greenhouse temperature. And we have a prefactor in units of temperature of 280 Kelvin. And then we're going to have a fourth root, because this is coming out of the Stefan-Boltzmann law, which has temperature to the fourth power. So when you flip that around to solve for the temperature, you're going to wind up taking a fourth root. So I have a factor of 1 minus the reflectivity of the object in the solar system over distance from the sun squared, and then that is all under a fourth root. And d is the distance from the sun in astronomical units, and reflectivity in the way your book writes it out, it's not even given as a variable. We're just going to leave it as a word. So reflectivity is the fraction of light reflected. And so then 1 minus reflectivity is the fraction of light absorbed. All right, so let's try a couple examples using this. Home sweet home. What will be our radiative equilibrium temperature on Earth? So hopefully I don't have to say this, but we are 1 astronomical unit away from the sun. So D is just 1. And then you can look up in your textbook the reflectivity for Earth. It's actually fairly high. It's 29%, so that's as a fraction 0.29. And we try to find this no greenhouse temperature, so the temperature Earth would have just coming into equilibrium with the flux of energy from the sun. If there were no no impact from our atmosphere. So we've got our 280 Kelvin. I'm going to have 1 minus 0.29, 1 squared. That's all to the 4th root. And when you calculate that out, I got that to be 257 Kelvin. And then putting that into Celsius, you need to subtract off 273 because 0 Celsius is 273 Kelvin. So that tells us without any greenhouse effect from our atmosphere, we're getting about minus 16 degrees Celsius as the average temperature for the surface of the Earth, so well below freezing. So thankfully we do have a greenhouse effect that raises the surface temperature of Earth on average about 30 degrees Celsius above that. So we're above the freezing point. Let's try another example. It's a little bit more complicated. You want to find what distance away from the sun, so we're going to solve for d that a comet is going to sublimate at. And sublimate just means it's a phase transition where you go just from solid into a gas and you skip over the liquid phase of matter. And that's appropriate for a comet because the pressure is very, very low. And so that outgassing from a comet, or its ices from the that dirty snowball model of a comet, where those ices change into gas, produce the coma and the tail. It's going to happen at a temperature of about 150 Kelvin. And consistent with the dirty snowball model for comets, comets have a pretty low reflectivity. Not that far off from asphalt. So reflectivity is about 5%, so 0.05. So absorb 95% of the sunlight and reflect 5%. So we use our equation to find the equilibrium temperature, and we actually know both temperatures. I'm going to have 150 Kelvin on one side and 280 Kelvin on the other side. 1 minus 0.05 is going to give me 0.95 over distance squared. That's all under the radical for the 4th root. I'm going to rearrange this in a couple steps to get the distance all by itself. 150 Kelvin over 280 Kelvin raised to the 4th power. To clear the 4th root, it's going to give me 0.95 over the distance squared. And I'm going to have a pure number on the left-hand side now. This Kelvin cancels out with Kelvin. Get the distance squared by itself on one side. So it's going to be 280 over 150 to the 4th power. And then I clear the square by taking the square root of both sides. It's going to give me a distance is square root of 0.95, and square root of something to the fourth is going to give me 280 over 150 squared. You put that in. I got that to be 3.3. So a comet will have its ice is sublimating into gases, so it starts to build up a tail at about 3.3 astronomical units. That's where we would expect comets to turn on. Once they go around the sun and go back out, that's where comets should shut off and become little snowballs again. And that distance also should make some sense because that's about where the frost line is. You're looking at a distance away from our sun that puts it between the orbits of Mars and Jupiter.